I had an interesting weekend. I'll say that.
Anytime someone says they had an interesting weekend, it usually does seem to be so.
Let's just say I didn't leave the room until 5 a.m. on Sunday. I remember seeing so many drunk blondes with them.
Drunk blonde?
Yes, I was the TV. Saturday night, Sunday morning. But it was fun. That's why I went to the bonfire for was to do TV. No. I was a DD for the person who threw the bonfire.
It's minding its own business. Leave it alone. Don't kill it. No.
Are you going after that harmless spider that was walking around over there?
Yeah.
It was not
I don't mess with spiders.
He looked at me and said, "You have strong." I was like, "Yeah, sure." You can see something. Spiders kill you. I was like,
All right.
Let's see here. Eric, Embry, Taylor,
no, I was
Bobby.
gonna go home anyways because I had a friend that could have driven my truck.
Lucy. We're missing a bunch.
So I looked at that house, I was like, "Please take this truck back, Bill." And then we went to.
All right.
And I kept back.
Okay.
It's either Pop-Tart or strawberry.
I knew someone who literally gives me acorn.
Well, I started the Pop-Tart one because he was trying to on, the first time I met him, they were calling it Pop-Tart, and wasn't the Pop-Tart, so I should call it Pop-Tart. And then Sam calls him strawberry because he's got like a burn mark on his
This kid literally in English class, like seventh or eighth grade, he was asked what tree do acorns come from, and he said an acorn tree. So we just start calling it acorn because of it.
Remember our friend's Zach's apartment, and Pop-Tart was asleep, and Kevin got the snake out of the cage. I was like, no, the snake was in front of me. Oh, I know. It was so funny. I love snakes. He's like this big right here. Look, and the snake is.
Oh, I had a snake that was like this big. That was got around this snake and was wrapped around my neck.
I'll get
About
about
that big.
I'll get about 6 pounds.
It's about
Small fire. And some sort of.
Wait, you don't have that?
No, it's
Oh, yeah, we can. Pull mine out.
I got 3 hours.
I don't think I have a 3, so.
Can't mess it up now. I've done
Not 3 more. No, that's English. That's like English. That's English.
That's right here.
So you have
It's not
like.
like everything.
No.
Trying to see if anyone else will come.
Well, we've lost Eric and Daviana.
All this.
Eric went to the bathroom because he just got out of classes.
No, okay, good, 'cause I haven't done like.
Maybe I was just like, nope, I'm out of here.
Yeah.
It's not.
All right. All right, why don't we go ahead and get started? I think there's Eric, and I think Daviana will be back in just a minute. We're going to go ahead and get started. Today's assignment is actually pretty manageable, I think. I think you guys will not have just too much of a battle for it. I'm going to try to do it on the screen over here more than up on the board just because we're recording the screen today instead of using the camera. Today what we're doing is rational functions, and rational functions are wild. There are so many weird types of graphs that you'll see with the rational functions that you won't have seen with other types of functions. Rational functions are functions where there is a numerator that's a polynomial and a denominator that's a polynomial. So they're like a fraction with the top and the bottom are both polynomials, like what we've been learning about so far. So far, these kind of equations, I mean, other than they look kind of messy, they don't seem like they're going to have all that much strange going on. But actually, their graphs will be really wild. And a big part of what we have to do is just sort of getting the idea of their graphs under control. But they are a function just like any other function, and they can have things like a 0 to them. I'm going to go ahead and make a new one over here. Let's just say f of x is equal to, I'll make a numerator that is, how about x squared plus 4, and a denominator that is x plus 1. Let's do something different. How about x minus, well, that didn't help. And add more to this. That help? No, what am I doing wrong here? All right, so like for example, this is a good example here. So does this function have any real zeros? No, because it doesn't have any place that it's crossing. Yeah, at least on the part we can see here. I guess I could back out more, make sure, because some of these graphs will be pretty wild. Let's see here. Where do I zoom out on this one? I'm going to go back to normal size here. And yeah, this one, I mean, I don't think this one is going to ever cross the x-axis. So this one wouldn't have any real zeros. The graphs are just really hard to predict what they're going to look like. Let's try adding an x cubed. Oh my goodness, x cubed. Right there. All right, here's one. Look how wild these graphs get. This is so strange. But this one clearly has a 0 here at this value. And in fact, there isn't like a lot of magic to figuring out where the zeros for these things are. The zeros, I mean, what's it gonna take to make this numerator equal to 0? Because if the numerator is equal to 0, the whole function is going to be equal to 0. So what you really are doing here is finding the zeros of this function, this x cubed plus x squared plus 15. And that we have done to death. Finding the zeros of a polynomial is not the end of the world. I mean, if nothing else, we could do it graphically by putting x cubed plus x squared plus 15 into the little calculator. Oops, sorry. Plus 15. It's going to be a mess here. There we go. That would be this green function right here. And we would say, oh, look, it has a 0 here at this value. So therefore, the whole function has a 0 at that value. The zeros of the rational function will be wherever the zeros of the numerator are. That makes sense, right? Any place if the numerator goes to 0, the whole thing is going to go to 0. What is going to be a bigger mess is when the denominator is equal to 0. Any place that the denominator is equal to 0, we're going to blow the whole thing up, right? It won't have any solutions. Let's actually see what happens there. Let's see, where would this denominator be equal to 0? Looks like it's going to be equal to 0 at x equals 1. All right, I'm going to turn this function back off here. Here, I'll even draw a line at x equals 1. Look what happens to this function at x equals 1. It blows up to infinity. That makes sense, right? As we get closer and closer, at x equals 1, we've got a divide by 0 problem. But the closer and closer we get to x equals 1, we're dividing by tinier numbers, and it's just going up to infinity. So we have two very different things happening depending on whether the numerator or the denominator is going to 0. If the numerator is going to 0, that's just going to be a place that this rational function crosses the x-axis. If the denominator goes to 0, that's going to be a place where the function blows up towards infinity or negative infinity. We have a good word to describe what happened here where this function got closer and closer, closer to, as we got closer and closer to x equals 1, it blew up towards infinity. We would say that x equals 1 is a vertical asymptote. Vertical asymptote. That is a line that our function gets closer and closer and closer to, but never quite crosses, as it just goes up towards infinity or down towards negative infinity. Yeah.
Cindy says she can't get on.
Okay, tell her I'm recording. I wonder why she can't get on. All right. So if you have some kind of function that has a numerator and a denominator function in it, wherever the denominator goes to 0, those values of x where the denominator goes to 0 are going to be where there are vertical asymptotes on these rational functions. The function can also have horizontal asymptotes. Let me see if I can make a simple horizontal asymptote example. I'm going to get rid of these ones we've put on here so far. Let me see here. How about at this function? What about x to the 4th power plus 2x plus 9 over x? How about 3x to the 4th power? That'll do. That'll do. Notice this function here has a horizontal line that it approaches but doesn't cross. Now, I'm going to tell you, we'll know in just a little bit here that that line is at x equals 1/3. But you can see as we zoom in on it, we get closer and closer and closer, but never actually cross it. Now, I want to be clear about something on this line here. I mean, we don't cross it as we go off towards negative infinity and as we go off towards positive infinity. In this case, I know they can't see if they watch the recording, but something could have happened here in the middle that crossed it. But I mean, as it goes off towards infinity, the line just sort of approaches that curve, that straight line rather. Those are called horizontal asymptotes. And we're going to learn some rules about figuring out where the horizontal asymptotes are. Again, we're just working on ways to describe these equations and describe the graphs of them. Because the graphs for these rational functions are going to be pretty wild. Now, on page 144 of your book, you have a blue box with yellow highlighting that is the set of rules we need. Kind of like the leading coefficients test. There's kind of a lot of detail in this box. Now, at this point, my guess is the leading coefficient test is something you remember that was the whole business of smiley face, frowny faces, and so on. That kind of stuff you probably have managed now. But if for some reason you don't, at the test, you're going to have the book. Open book will be okay. Right? And in the same way, this blue box on page 144, the truth of the matter is, if you try to memorize this thing, you'll probably make mistakes. I mean, I would. So I can understand that if you don't want to memorize it, that's fine. All right, but it's telling us that for any rational function with a numerator and a denominator function there, the graph has a vertical asymptote anywhere there's zeros in the denominator. That's what we've been talking about. Like in the case of this function that's up there right now, where am I? We have a denominator here. That denominator will have a value of 0 any place x is equal to 0. And you can see this function blows up at x equals 0. It has a vertical asymptote there. The question is, what is the horizontal asymptotes? And you can see there's sort of 3 rules here. And the trick is to notice what it means about these numbers n and m. N is the degree of the numerator, and m is the degree of the denominator. Look at rule A. If n is less than m, the graph has one horizontal asymptote, and it is the y-axis. Let's pick one of these ones that I've made already. Do I have one that exactly illustrates that? Yes. No. If n is less than m, I'm sorry, if n is less than m. Okay, so how about this one? Here's my numerator, it's 6. I'm sorry, its degree is 5 rather. And here's the denominator, its degree is 6. So the degree of the numerator function is less than the degree of the denominator function. If I turn that one on, first of all, what a weird graph. But look what we got. We've got a horizontal, just like rule A said on page 144, we've got a horizontal asymptote that is the y-axis, or the x-axis rather, I'm sorry. It's the one, so the line gets closer and closer and closer to that axis. Notice it does blow up apparently at x equals 0 and someplace else over here. I'm not quite sure where yet. I'd have to find the zeros of this equation. But I can see that it blows up 2 places and has a horizontal asymptote. What a weird graph. Your rule B says, what about if n is equal to m? If the degree of the numerator is equal to the degree of the denominator. And I've got one like that right here. And on this one, it says you'll take the leading coefficient of the numerator, in this case of 1, and the leading coefficient of the denominator, in this case of 3, and your horizontal asymptote will be at 1/3. It's just the ratio of those 2 leading coefficients. Let's see what happens. Oh, again, what a weird graph. There's a weird little step in it and so on. This is a weird graph. But it has a horizontal asymptote here, apparently at x equals 1/3. Let's actually, I'm sorry, y equals 1/3. And we could actually draw that in there like that and see, yep, that's where the asymptote is. As it goes off to infinity, it goes one or the other. And your rule C on that page is if n is greater than m, if the degree of the numerator is greater than the degree of the denominator. And it tells us then there is no horizontal asymptote. And so here's one I got. This one has a numerator of 3. A numerator degree is 3, and a denominator degree is 2. So the degree of the numerator is greater than the degree of the denominator. And if I turn this one off and turn this one on, again, it's a very weird graph, but it doesn't have a horizontal. It doesn't have a horizontal asymptote. It has a weird asymptote that's actually at a funny angle, which is a different thing we can figure out, although that doesn't actually come up in pre-calc. But it doesn't have a horizontal. It doesn't have a horizontal asymptote. But once we start applying these rules, I mean, actually, things like, for example, I'm going to just change some of these things to just constants I can play with. Notice, no matter what I do to the numbers, it still doesn't have a horizontal asymptote. All these functions are so strange. Never actually has a horizontal asymptote, though, because no matter how I change those coefficients, I still had a degree, a numerator degree that is higher than the denominator's degree. So we never actually got to have a horizontal asymptote at all. In contrast to, say, this one over here, let's see, that one had a numerator degrees that was less than the denominator degrees. So it shouldn't matter what I do here and here and here or any place else. The numbers don't matter. Well, they matter to what the function overall looks like. But notice, no matter how I change these values, I still have a horizontal asymptote that is at the x-axis. And over on this one, where I had the numerator and the denominator degrees were both the same, again, I could put in numbers here to change. They do change the appearance of the graph, but they don't change the fact that it still has a horizontal asymptote at that same value, the ratio of the leading coefficient of the numerator to the leading coefficient of the denominator. You get all these weird graphs. Rational function graphs just get so strange. Fortunately, today we're mostly just experimenting with them and getting a sense of where their asymptotes are and so on. So if I slip over to done. I'm just going to show you what the problems look like here. Here's group 1. It says, does this graph have any horizontal asymptotes? All right, well, I see the wheel spinning already. And students say, let's put this into Desmos and just see. And I don't necessarily hate that answer, except for one thing. Does that look like that's going to be a lot of fun to put into Desmos? I deliberately made it awful. Because I'd rather you use the rules in the book that says that, let's see, the degree of the numerator is higher than the degree of the denominator. So I go back to page 144. If the degree of this, it should have no horizontal asymptotes. So our answer over here is going to be does not have any horizontal asymptotes. And you'll see I made a mess of all of them. Again, the program writes it. I just wrote the program. But all of them should be a real mess to code up. No, it won't let me pick them. I've never quite understood why sometimes, if you haven't figured it out, sometimes you can actually copy and paste this equation into Desmos. But if it's at all complicated, it doesn't like it. Anyway. I should show you that actually. Let's do it the other way for a second here. I just copied this equation in Desmos. Let me pull up a notepad real quick here that I'm not already using something else. Let me show you real quick here. That's actually the code in a language called LaTeX for that equation. In fact, it's the code that I use on the website, and LaTeX is actually a good code for coding up math. And so they sometimes will let you cut and paste back and forth, which in this case would have made this a whole lot easier, but it's not letting you do it anyway. I didn't stop you. But yes, if you could just cut and paste this equation into Desmos, then all of a sudden there'd be almost no work to these problems at all. All right, so those are what the first group of problems look like. The second group of problems wants to know if there's any vertical asymptotes. Those first problems were about there was any horizontal ones. Now there's questions if there's any vertical asymptotes. Vertical asymptotes happen where the denominator is equal to 0. So what you really need to do is find the zeros of this denominator. And you can do that by whatever method you like. But if I'm not mistaken, all of these factor pretty easily. Let's see here. They multiply to negative 14, but add to 7. So I think it's going to be x minus 7 and x plus 7, x minus 2. So the zeros of this equation are at negative 7 and 2. And we would just find that one on here. Again, making the graph as a way of checking your work sounds like a spectacularly good idea. I mean, however you want to do that. So we have a group that's about finding the horizontal asymptotes and a group about finding the vertical asymptotes. What about the domain? Oh man, you keep throwing this word domain around. Remember, domain is the set of all x values that work in this function. And on these rational ones, the domain generally extends from positive infinity to negative infinity. The problem is there's usually a couple numbers along the way where it blows up. If you're looking for where they blow up, just find places where the denominator is equal to 0. Again, we just need to factor that denominator. Let's see here. Numbers that multiply to 18 but add to negative 9. I think that's going to be x minus 6 and x minus 3. So the function blows up at 6 and 3 because those are the places one of those factors will be 0. And we're dividing by 0 then. So you just find the one where that is. I guess it was this one that I actually circled. All right. So the domain, we're just basically finding out the places where the function doesn't work. We can't plug in the values there. And then I think the next one's a review, if I'm not mistaken. Let's see. Oh, no. It isn't. All right, let's see what we got here. The Game and Parks Commission introduces deer into a newly acquired state game land. Who thought I could mix in story problems on this planet? The population and of the herd is given by this function. N is equal to this stuff that's got some t's in it, where t is the length of time since the introduction of the deer. What is the limiting size of the herd as time increases? Now, before we would actually make a graph of this or anything, what are we actually talking about when we mean limiting size? It's going to be a horizontal asymptote. As we get out towards infinity, the deer aren't going to keep growing and growing and growing and growing and growing until there's like a million billion deer out there. This is a logistic curve. It's going to grow and then eventually kind of level off. And we're just trying to find the horizontal asymptote. Well, wait a minute. It's just a horizontal asymptote problem. Huh. The horizontal, let's see, wait a minute. What is the degree of the numerator? It's just got a t in it. So the degree of the numerator is 1. The degree of the denominator is 1. It's one of those ones where the degree of the numerator and the degree of the denominator are the same. I better look that up on page 144. If the degree are the same, then it's just the leading coefficient of the first one divided by the leading coefficient of the other one. This one's leading coefficient would be 36 if we multiply the 2 by 16. This one's leading coefficient is a horrible 5 over 100. With a little patience, a person could even put that into the calculator and be careful. I'm just curious as to what it looks like. I'm going to get these off of here and make another one. Here's my population of my deer. It was 18 times 6 plus 2x. I'm going to use x's instead of t's. 1 over 5 divided by 100 t. Oh man, where did t x? Back out of here for a little bit. Back. Hey, look. The deer start off at low population, and at first they grow really fast. Keep in mind the population here, the scale here is really big. This is 500 years here. So at first the population goes fast, but over long periods of time, the population is going to level off. It looks like somewhere around 700. It's 720, if you actually did the arithmetic up there. Yeah, 720, that could be right. Yeah. She's saying that if we actually did 36 divided by 5 over 100, you get 720. So over the long period of time, there would be 720 deer in the park. At first, we just put a few in there and they'll reproduce, but by the time they get to about 720, that's as many deer as there'll ever be. Natural populations tend to grow with curves that look something like this, because after a while, why doesn't the deer population just keep growing and growing? They start running out of resources. The forest doesn't support that many. At some point, the wolves figure out that's a great forest to live in, and they come eat more of the deer. At some point, the hunters figure out that's a good forest to go to, and they start shooting more of the deer. At some point, the population levels off. Okay, so wait a minute. We got 4 types of interesting problems here. I think it's actually pretty manageable, though. So for today, you have an exit ticket, a slightly longer than usual exit ticket, because I added some reviewing questions, because I think overall, the average on the quiz was a little low. So I added some extra questions on there that kind of added some reviewing. And then you have these 4 groups of problems. That should be all we need. All right, so I'm going to go ahead and stop sharing. And I'm going to go back over to my meeting. And it's been recording, and so I'll have it up shortly for the other folks. And you guys can work on the homework. I'm going to go ahead and stop recording. Stop.